Hi everyone. Today I'm going to present our paper Bayesian generational population-based training. I am Xingchen Wang, and this is a work jointly with Tom Lu, Jack Packerholder, Philip Ball, Wu Wen, Bingxin Ru, and Michael Osborne. RL has seen great progresses in the past decade, but one limiting factor has its sensitivity to hyperparameters. And automated reinforcement learning, or AutoRL in short, is designed to address this. However, AutoRL has its own challenges. For example, in RL, we also often have non-stationarities, as optimal hyperparameters and architectures can shift during the training process. And secondly, AutoRL so far has mainly focused on tuning hyperparameters, but not architectures. So in this work, we propose Bayesian generational population-based training, or BGPBT in short. So this is a general purpose AutoRL algorithm based on the BBT paradigm, but it tunes both architectures and hyperparameters. So the first innovation is we use model-based hyperparameters and architecture exploration using high-dimensional mixed-space time-varying Bayesian optimization agent tailored to this purpose. And secondly, we also enable discovery of curriculum of architectures made possible with generational training via distillation across networks of different architectures. And finally, we experimentally validate our algorithm on Bragg's environment using PPO. So before I talk about BGPBT, I would like just to spend a few minutes talking about the BBT paradigm. So in BBT paradigm, we often start multiple agents and train them in parallel. And we initialize with random architecture, random hyperparameters and weights of the same architecture to fill the population. And at a regular interval, we conduct exploitation and exploration step. At the exploitation step, we copy the weights of the best performing agent to the worst performing agent. And at exploration step, instead of just copying over the hyperparameters of the best agent, we also randomly perturb them from the best hyperparameters in the hope of finding even better one. So in a sense, this is similar to an evolutionary approach. So on that side, BGPBT proposed several improvements. So firstly, at initialization, we not only have random hyperparameters and weights of the same architecture, the different agents in the population can also have different architectures. And exploitation step, not only the weights, but also the architectures of the best performing agent are copied over the worst performing agent. So as you can imagine, towards the end of the generation, agents of this population will typically only feature a few different architectures that are deemed to be good. So this, in a sense, creates an effect similar to successive halving. And at exploration step, the hyperparameters are not suggested by random, but instead we use a time-varying high-dimensional BO agent. And we use a time-varying cosmopolitan agent, which is a state-of-the-art method in mixed-space high-dimensional Bayesian optimization. It has three key features. So firstly, it has trust regions. So this means all new hyperparameters will be proposed in a close neighborhood to the best hyperparameters seen so far. So this avoids large jumps in hyperparameter value, which could lead to instabilities in reinforcement learning. And secondly, it supports mixed input. This is important because we have both ordinal and continuous hyperparameters. The ordinal hyperparameters include, for example, the number of updates per epoch, whereas continuous hyperparameters include things such as the learning rate. And it's important that we treat different hyperparameters differently. And lastly, it also supports high-dimensional BO. This is important because we tune more than a dozen hyperparameters on the fly, a number much larger than previous PBT approaches. For example, PB2 only tune 4 hyperparameters. And another important innovation in BGPBT is the introduction of the notion of generations. So as discussed, in the first generation, we simply fill the population with random architectures. But in subsequent generations, we use another BO agent to fit on data of previous generation to suggest new architectures. And we also supplement that with random architectures to ensure that we're exploring the architecture space properly. So a question would be, when do we start a new generation? So in this paper, we use a simple heuristic that when the training in the previous generation stops improving, or when a prefix maximum number of time steps per generation is reached. And to transfer knowledge between the generation, we use unpolicy distillation with best agents of previous generations as teachers, and we distill that to a diverse set of new population in the next generation. And putting them together, here I'm showing an example of BGPBT running on half-cheetah environment. And as you can see at different points in training, you can see that BGPBT is selecting different architectures and hyperparameters. And we also see that distillation and generational training enable continual improvement of the agent throughout the training process. And for the experiments, we conduct an experiment on the Brax environment with PPO. And here we're comparing against a random search. So I have both RSZ and RSJ. So the difference is whether we are only searching over the hyperparameters conditional on the fixed architecture recommended by the Brax authors, or we search both architectures and hyperparameters. And we also compare against other previous PBT methods, such as the original PBT and PB2. And we can see that BGPBT outperform all of them in all environments. We also compare against sequential Bayesian optimization. So for sequential optimization, given a set of hyperparameters, we train the agent for a full 150 million steps in a static manner. And we use a final reward as the objective function for the BO, and we run BO loops sequentially. And we can run it both on hyperparameters only, conditional on the Brax architectures, or the joint search space of hyperparameters and architectures, similar to the random search baseline I mentioned before. And we use SMAG for 50 iterations. And the two different versions are marked by BOZ and BOJ in table 2. And as you can imagine, running BO in this manner is much more expensive than our method in terms of both GPU hours and work clock time. But BGPBT still performs strongly, even though the sequential BO baseline takes a much costly computational expense. We also conduct ablation study on both key components introduced, namely the tailored BO agent and neural architecture search in table 3, and we do find that in a majority of cases, both components will lead to improvement in performances. And finally, we'll also investigate the learn schedules. And here I'm showing the schedules of architectures and hyperparameters learned by BGPBT on the end environment. And on the architecture side, we do observe that the BGPBT is selecting architectures with increasing policy net size as training proceeds. So this matches our intuition that in an early stage of the training, maybe a smaller architecture is favored to ensure fast learning, but at a later stage, we want to increase the network size so that we can model more complex behaviors. And on the hyperparameter side, we found that BGPBT quickly anneal the learning rates and also increase the batch size. So those are the practices very similar to the common practices in both deep learning and reinforcement learning. So this is a demonstration that BGPBT can discover powerful schedules of hyperparameters without human intervention. So in conclusion, in this paper, we propose BGPBT that tunes both hyperparameters and architectures in reinforcement learning simultaneously using a tailored BO agent and generational training. And we've shown that BGPBT led to significantly improved performance on the Brax suite of environments. However, we do recognize there are several limitations and future works that could be done. So firstly, although BGPBT automate the reinforcement learning hyperparameters, there are still PBT hyperparameters themselves that remain. Examples include the number of the intervals where we do PBT iterations, and our future direction will be how do we automate those hyperparameters as well. And secondly, we believe there's still room to improve architecture selection because sometimes, as we've shown in ablation studies, performance can be better without NAS. And thank you very much for your time and have reached the end of my presentation, and I look forward to seeing you in the conference.